Hello, I'm here today to talk to you about the steps of the scientific method. You should be watching this video if you need extra reinforcement, if you were absent from class today, or if you're on quarantine and you need to have a direct instruction on the steps of the scientific method. So the scientific method is a method of problem solving involving observation to test a hypothesis. And this is not the first time you've ever heard of that fancy H word we call hypothesis. So your first step is to determine a problem or a question that you know that you want to test. And you're going to state that problem as a question. It could be anything from something in your everyday life to something about how plants grow, which is the example that I'm going to kind of use throughout the lesson today. And you're just going to figure out what your question or your purpose about around your research may be. So, of course, speaking of step 2, you need to research. So after deciding on your question, you should complete some research to discover what background information is needed to perform the experiment. Use reliable resources to do your research. So databases, you're going to visit the library, you're going to talk to a specialist in the field. They're all great ways to get your research so that you have a better understanding of whatever the topic may be. Step 3 is to actually form that hypothesis. So we usually say that hypothesis is an educated guess. So you're not just making a guess. You have some prior knowledge based on your research to try and make an assumption based on what you know. Okay, so based on your research, you're going to make an educated guess that answers your question. This could be a possible solution to a problem or an if-then statement. It's really important that you identify which we're going to talk about in the next couple slides, variables. And if you write your hypothesis in an if-then format, it's really clear by the end of the experiment if yes, you can support your hypothesis or no, you cannot. So that's the if-then format of the hypothesis that's important. So step 4 is probably a lot of students really like this step because this is where you actually do your testing and your experimenting. But you also have to design a good procedure. You have to make a list of directions for testing your idea or hypothesis through a controlled investigation. Good controlled investigations have variables and groups that you can identify so that it's easier for you as a scientist to identify why there was a change. So these should be detailed so another person can follow your directions and perform the same exact experiment. So all the tiny little details that you do in this experiment need to be recorded. It needs to be able to be replicated and get the same results by somebody else, whether in the field of science or just another student, just so that you can get clear-cut results to see if, in fact, your hypothesis is correct, you can be supported or rejected. So think, could someone else do the same experiment based on your written directions? Okay, so you really, really need to provide a lot of detail when you're designing your procedure for your experiment. While completing your experiment, you must make observations using your senses. So depending on what the experiment may be, so sight, taste, touch, smell, you're using your senses to gather information about whatever you're looking at. And then you have to make a list of all the materials you need in your experiment. Something as simple as, for example, with plants, the soil, you need the containers, you need the sunlight, you need the water, you need the seeds, right? So you need to be explicit with what sort of materials you need for this experiment. And there's also going to be something in this experiment that you're going to design, and it's called constants. Constants are basically kept the same throughout any experiment. So if you look this, and again, I'm coming back to that plant example because it's easy for students to understand. If you're looking at a couple different, or you're looking at a plant and you want to see if, in fact, color light is going to influence how much they grow. All of those plants that you're going to put into the different colored light, whether it's white light, whether it's black light, whether it's purple light, green light, red light, whatever it may be, they all have to be the same. So you're going to have the same amount of soil in each of those cups. You're going to have the same amount of seed or the same seed in all of those cups. They're going to get the same amount of water that you would have to measure, the same amount of nutrients, right? If you're going to add some sort of fertilizer, it has to all be the same amount. The only difference for your constant, or the only thing that should be the difference, is going to be what we're going to call our variables. So let's talk about our variables. These are four things that many students get kind of tripped up on. So it's called the independent variable, the dependent variable, the control group, and the experimental group. So let's first talk about our independent variable. Your independent variable is typically the variable representing the value being manipulated or changed. So when I think of that word manipulated, it's you as a scientist. What are you trying to control? What are you trying to see? In that example that I just mentioned with the plants and the different colors of light, that's going to be your independent variable. I want to see if I shine different colors of lights on these plants, if they are going to change their growth. Okay, so that would be the independent variable. So what does the scientist change? All the different colors of the plants, of the light on the plants. When you're making a graph, you do it on the x-axis, which is the axis that goes across. And then it's always the cause of the change, the cause of that change. On the other hand, that's your independent variable. Your dependent variable is sometimes referred to as your responding variable, and it's the observed result of the independent variable being manipulated. So what am I going to collect data on? What am I going to measure? So in the case of the plants with the different colored light, the dependent variables, how much is that plant going to grow in all of those different settings? So in the white light, in the green light, in the purple light, in the red light. Which one grew the most, and in what capacity over a 3-week span did it change? That's what is going to be my dependent variable. It's on the y-axis on the graph, which is up and down, and it's going to be the effect. So these are some examples. So the amount of time you study will make a positive difference on your next test score. So your independent variable, what are you going to change? What are you as a scientist going to change? So it's the amount of time you're going to study. You're going to spend lots and lots of time to study to be successful on your science test. The dependent variable is, what are you measuring? Well, in this case, you're measuring what your score is going to be on that next test. So that's your independent and dependent variable. Okay, here's another example. The temperature of the water was measured at different depths of the lake. So the independent variable, the thing that was changed, was the temperature in degrees Celsius or whatever value you're looking at. That was the difference. And then the dependent variable is the depth. That's what you're going to record or measure to see if there was the cause versus the effect. So the cause is the temperature on the depth of the lake. So a good experiment will have clearly identified groups and variables. And you're going to need two groups, a control group and experimental group, to make sure that your variable is a good one. Both of your variables, your independent and dependent variables, are measurable, they're attainable, and they're actually causing a change. So the control group, and this is an important definition, is the standard against which the other conditions can be compared to in the experiment. So it's going to be, sometimes it's the control group. So you always have the control group, and then you have your experimental group. So the control group is the group separated from the rest of the experiment where the independent variable being tested cannot influence the results. Okay, so it's not going to influence the results. It's the group without the independent variable. So if the example with the plants and all the different colors of light, the control group's going to be a group without light. Okay, so you're going to put a plant somewhere dark without any sort of light, not white light, not green light, not purple light, whatever it may be. The experimental group is the group in the scientific experiment where the experimental procedure is performed. This group is exposed or given the independent variable being tested, and the changes are then observed and recorded. So obviously, if you put a plant in the dark, probably not going to grow, right? Because you need light for it to grow. So in your experimental group or groups, right, you can just have one or you can have a couple experimental groups, the different colors of light. So red light, yellow light, purple light, white light, which one will allow that plant to grow the most? So that's your control group versus your experimental group. So of course, these are two examples of the two groups, so you can kind of clearly identify them in scenarios. So it says, in medicine, many drugs need to be tested using clinical trials before the FDA approves the drug. Case studies are created in groups of people are usually divided into two groups. One getting the placebo, which is like a pill or the medicine, but does not contain the active ingredient or the drug. And one group getting the medicine with the active ingredient or the drug. Record your results and data is collected and then analyzed. So the control group in this example is the group getting the placebo, right? Which is basically a pill or medicine that looks exactly like the drug, quote unquote, but it doesn't have that active ingredient. And then the experimental group would be the people that are getting that pill or that drug with the active ingredient. So you have some sort of a comparison or a standard to compare it to. That control group is going to be really, really important. You want to make sure that that change that occurred was because of a result of the independent variable and not because of anything else. Here's another example, kind of silly, but scientists want to see if silly soda affects the elderly. Adults at the nursing home are split into two groups. One group will get silly soda and the other ones receive water. So the control group is the group that gets the water, and the experimental group is the lucky group, I guess, that gets the silly soda. And then they would look at the results, see how it impacted, the different elderly individuals, and then collect data that way. So again, these are just a couple different visuals. I know I'm a very visual learner, so you can kind of see some examples of the control group versus the experimental group. So with that being said, this is a video that should pop up that I think was a really, really good one. So please watch this. It's about a 3-4 minute video. So please watch that as an overview. Oh, 2-minute video.
When scientists set up.
So after you conduct your experiment, you figure out your variables, your groups, you get your materials, you made your observations. Now you're going to record your results and collect your data. So it's kind of time lapse, right? Depending on how long your experiment may take, it might take a short period of time or may take a long period of time. So as you perform your experiment, you're going to collect that data. Data can be found in a variety of different ways. It could be quantitative, which is kind of like numbers, or it could be qualitative. So it's going to be something more like descriptions or how did it make you feel and things like that. And both of them are very important in any experiment. So using this data, you may make a judgment or opinion inferred from relevant facts. So the facts that you just got from your experiment, and you're going to make a final summary based on what you found. Then you're going to check your results. You're going to kind of revisit your hypothesis and say, yeah, my hypothesis was correct, or no, my hypothesis was not correct. And then, of course, if you reject your hypothesis, you're going to need a new hypothesis. Maybe you found something else that was causing the change, and it wasn't actually the color of light that caused the plants to grow in under different scenarios, right? So you would that's kind of your step 6. Check your results and analyze your data. And then you're going to make a conclusion based on what your experiment was all about and what you found. And again, in science, the beauty of science is that you don't have to have a correct answer. As long as you kind of question yourself again and kind of come up with some more information, that's the whole beauty of having science. As long as you kind of support it, give me a conclusion based on what you found, based on your data, then you're in a good boat. So after completing your experiment, you will make a judgment or an opinion inferred from relevant facts and write that as a final summary. So there's another little video clip that I thought was pretty cool. It was a review of the scientific method, so please feel free to watch this. I like this comparison of using the scientific method in your world. So if you look here, if anybody's Italian, you know this all too well, but when you make red sauce or gravy, depending on what your ethnicity and your background is, your observation is that spaghetti sauce should be red. So you're going to say, all right, I'm going to make some spaghetti sauce. I'm hungry. I want to try out this new recipe. So you're going to test. You're going to put some tomato sauce in with a bunch of ingredients. You're going to try it out. You observe results that I don't like it. It's too bland. What can you do if it doesn't taste good? You're going to add something to it. In this case, you're going to add some garlic. You're going to mix it up. You're going to let it heat, and you're going to try it again. How does it taste? Okay, tastes better now. That's good for my recipe. And then you could figure it out, and then you can reproduce that recipe. So that's, again, just everyday life, everyday science. Here's the same thing. I know a lot of you guys are into cars and want to be future mechanics. So the engine won't turn over. So you're like, all right, well, there's a variety of different things that could happen. Why isn't that engine turning on? Okay. Is it because I'm out of gas? I'm out of oil? The engine's bad? What could go wrong? So, all right, battery's dead. What can I do? All right, well, let me try and replace the battery. The observed result, the engine now works. So you were unlucky on this try because you figured out, or you'd made a guess based on your prior knowledge that it was just the battery, right? Do you need to revise your hypothesis? Do you need a new test? No, you don't, because you already figured that out. But if your battery stopped working, you put a new battery in and it still didn't work, then you'd have to go back to the beginning. Scientific theory, cars won't work without a fully charged battery, right? So that's, again, 2 examples of this in your everyday life. So hopefully you enjoyed listening. Again, this was just a reiteration of this notes on the scientific method. If you have additional questions, please feel free to reach out to your science teacher. We would love to help.